Assalamu alaikum, dear student. This is Dr. Aisha Nazuk here, and today we are going to cover the topic of regression analysis. Those viewers who haven't watched the video lecture on correlation analysis, they are strongly advised to watch the topic of correlation analysis. Also, watch the videos on standard deviation and arithmetic mean so that you can easily understand today's topic. It's a good idea to subscribe to our channel so that and turn the notifications on so that you will get important updates because Dr. Aisha Nazuk is planning to use this platform for long-term delivery of knowledge and information sharing. Okay, so today's topic is two-variable regression analysis. If you could recall, what was the purpose of correlation? It was, or it is, to know the strength of linear relationship between two random variables. Now the word uses linear relationship between two random variables. That is, if we plot the two random variables on a scatter plot, the pattern will be close to a straight line. Now, what can correlation tell is just the strength of linear relationship. It is not going to give you any mathematical equation that you can use to predict the value of one random variable on the basis of the other one, right? You don't have any formula. Correlation just tells you the strength of linear relationship. Even it doesn't tell which variable is dependent on the other. It just says that there is joint association between these two random variables. Now, regression analysis is a little bit different. Not only will it tell us which variable is dependent upon the other, it will also tell that what is the equation that can be used to estimate the relationship between those two random variables. Okay, for example, if the correlation between Human Development Index and the Gini Index, which measures the poverty or the income inequality, if the correlation between Human Development Index and Gini Index is high, then we will only say that they are mutually strongly interdependent, but we won't say whether poverty depends upon human development or human development depends upon poverty. This example may not be very clear for those who are not students of economics. So you can take any random variable. For example, your dietary choices, like the food you like. For example, there is a high correlation between your dietary choices and your siblings' dietary choices. Then you can't say whether your sibling choices are dependent upon yours or your choices are dependent upon him or her. I mean, of course, you can argue upon it, but statistically, you can't say it. So correlation just tells you that there is some association between the random variables. But correlation cannot tell us which of the two variables is dependent upon the other. And it can't also tell us, for example, if this dietary intake example, if your choice changes, what will be the impact on the choice of your sibling? Correlation cannot tell that type of answers. So in statistics, we call it that if one of the variable changes by 1 unit, what will be the change in the other variable? So these type of inquiries are possible under linear regression, right? So if our interest is to classify one variable as independent or the explanatory variable because it is explaining the dependent variable. So we want to classify one variable as explanatory or independent, while the other one as response variable or the dependent variable. Then we are looking for regression equation, which the general regression equation is the background concept is y, or the dependent variable is a function of an independent variable x. So this equation in A, it's a mathematical expression. Why it's mathematical? Because there's nothing random in it. It's just saying that if you know the value of x, you can exactly calculate the value of y. But you know that in practical scenarios, random variables are not that exactly or 100% predictable. You can estimate the value of one variable based on the other. So that's why in reality, we are looking for stochastic or random models. What does that mean? We are going to introduce a error component in this equation A. So let's see that error form of equation A. So you can write that you will introduce, I will explain this particular example as well, but you will introduce some random factors or random error in the equation. Right? For example, consider the case of dependence of marks on average weekly study hours. See, if you are studying, for example, 3 hours, what will be your average weekly study hour? So we have shortened it, abbreviated as AWSH. So if student 1 studies for on average, let's say 12 hours per day, I know that's quite seemingly insane, but I assume that it's a peak exam season. So student 1, both student 1 and 2, they are studying for 12 hours daily on average. But it is fairly possible that student 1 scored 9 out of 10 marks, while in same quiz student 2 scored 7 out of 10 marks. So why is this difference? It's actually because we cannot exactly calculate marks on the basis of knowledge about our study hours. We can estimate, but we cannot calculate. So this difference in marks between marks of student 1 and 2, this difference is due to some other factors that can influence marks. For example, student 1 had good health pattern, but student 2 developed headache on the day of quiz. Right? There's something purely random. That it's not, I'm not saying that that student is permanently having any disease, unfortunately. I'm just saying, suppose that that particular student faces a sudden headache on the day of quiz. Then the impact of that sudden headache will be stored in this random factor part. And this may be the reason that the marks of those students are different. I mean, this is not the only reason. I have given you one example. Therefore, in real world, functions or the equations are stochastic or statistical in nature. So we can rewrite the equation A that we just wrote above. Instead of writing y as a function of x, we write that y as a function of both x and u, where u represents all those random factors that can influence your dependent variable. Okay, now this form in B is still, I won't say this is linear because this is general function. Linear function will be when there will be no non-linear terms. For example, if I see this exposition or this illustration, now you see the power of both variable y and x is 1. So this is a linear equation. So this is a general representation of a linear regression equation where this a is any constant which we call intercept and b is another constant which we call the slope coefficient. So we can either write this way or we can write this way. Both are same. It's just that in the first form we have written that a could be positive, negative. So in this form we have written that a and b are, so if we just write with this equation, see that a and b are any constant, so that means they could be positive, they could be negative as well. Okay, we can expect the sign of the slope coefficient a priori, that is even before running the actual regression. I can anticipate that if I study more, I'm going to secure more marks. So that means that the relationship between y and x will be positive or increasing. So this coefficient on x will be positive. This is what I'm expecting. And why am I expecting this? Because theoretically, I am expecting that if I study more, I'm going to grade more, secure more marks. Now we come to the interpretation of A and B, that is the intercept and the slope coefficient. Okay, if I put a symbol hat on Y, that means that for the time being I am ignoring the impact of random factors. That is why I'm saying that this is now an estimated value of the dependent variable. You know that the random factors are there, but you cannot directly observe them because their occurrence is not predictable. So you don't have uh, readily available data on the random factors. So if I, for the time being, ignore the random error part or the random factor part, I can write this as y hat is equal to this. Okay, so what is the interpretation of this slope coefficient b? We will say that if x increases by 1 unit, y will increase by b unit, right? Or if x changes by 1 unit, y will change by b unit. We will also do this numerically. Then what is the interpretation of this A? If you put x is equal to 0 in this equation or in this y hat equation, if you put x is equal to 0, you get y hat is equal to A. So that means putting x is equal to 0 means you are ignoring the impact of 0 and impact of x, and you are saying that there are some other non-random factor that can influence your marks. For example, if it's a mathematics course, whether you have background concepts of mathematics, it will determine your quiz marks. It's not a random factors, right? Whether you study in groups or not, that can also influence your marks. So in other words, all things other than this x, their random effect is stored in U and their average effect is stored in A, right? So this is the interpretation. Before I practically run the linear equation or linear regression, let us check when we can impose the linearity restriction. Actually, if you are given any data, you always make a scatter plot of that data. For example, if we are given this data and we want to see whether this data is linear or not. So if I plot y versus x and suppose y is marks and x is the study hours, so this type of plot will come up and you can see this is not linear because this is sort of a inverse U shape, or you can say this is piecewise linear, piece A, piece B. So it's not linear, right? So for this type of data, if you have to run regression, you should divide the data into two equal parts. If you see this table, after this value 7, the relationship is being changed. For example, before 7, if x increases, y increases. But after 7, if x increases, y decreases, right? So if you have to, in practical scenario, handle these type of regression, maybe you can run two different regressions. I'm not expecting that in introductory statistics, student will be able to run two different regressions, but at least they should have an idea what is the purpose of scatter plot in determining whether the data is relevant for linear regression or not. So this data is not valid for linear regression if we use this as it is. Okay, so this concept I have already explained. Now coming that if we have these type of pattern, okay, suppose if the scatter plot are of these type, you can see this is a linear increasing relationship, this is linear decreasing. So if our points are, of course they won't be exact on the line, but if the lines points are clustered around a straight line, then you say that the data is linear and you can apply the linear regression. Okay, then linear regression is often called ordinary least square. And why do we call it ordinary least square? Is because, for example, if this is the scatter plot and these actual encircled points are your actual data points, and this straight line that which is passing through is the line of best fit. And how this line of best fit is determined is through some formulas that I will be sharing soon, that if you use those formula, you will be ensuring that you are drawing the line of best fit. For the time being, what you should know is the difference between the actual data and the line of best fit is UI, or the residual or the random error that we introduced initially. So these different black lines, the difference between each actual value and fitted value is called residual or the random error. But the problem is, how can I say whether a line is best fit or not? For example, if I add all the residuals, sum of residuals will, or the sum of random error will always be 0. No matter whether the line is best fit or not, no matter how you draw it, if you simply add the residual, the sum of residuals will be 0, or the sum of the random errors will be 0. So what statisticians have proposed, that instead of minimizing the sum of residuals or the sum of random error, the formulas that you will cover, and now they are based on the derivation or the background condition that the sum of the square of residuals or random error is minimum. This is the same concept that when we were doing standard deviation, we applied a square on the deviation, because if you don't apply the square, the answer will be 0. So what is it saying? That if we take this deviation, square it up, plus this deviation, square it up, and so on. So you're not going to practically do it, but you understand that is how the regression formulas are working. So under this formula, researchers have derived the formulas for regression. This is the formula for slope, right? I will also share the formula for intercept, and we will discuss a numerical example. Suppose we have this data and we have to fit an ordinary least square. So if we have to fit ordinary least square, first step is to draw the scatter plot, and we can see that all the points are clustered around a straight line, so we can fit the regression. So the formula for intercept is this: y bar minus slope times x bar, where slope is equal to this. So that means we need sum of x, sum of y, sum of x square, sum of xy. So let's compute these quantities here. So that's what I have done here. Xy, that is multiply these two columns, x square, that is square of this x column, and then we sum these and put in the slope coefficient formula, right? N is the number of pairs. You can see there are 5 pairs. Summation xy is the sum of this column, which is 490, and so on. You switch on the values and you get the slope coefficient is 2.5. Then the intercept is y bar minus b times x bar. What is y bar? Average of y. What is x bar? Average of x. So average of y is sum of y over number of values, then sum of x over number of values, and put in the slope coefficient, and you get that intercept is 5.1. So this is your final equation, that y is equal to a plus bx plus the random error. And if I apply hat on y, then I will skip this u part. Okay? If I apply hat, I will simply write y hat is equal to 5.1 plus 2.5x. That is, we are estimating that if we are given a value of x, then we can predict the value of y by putting that value of x in this equation. And the interpretation of this slope coefficient is, if x increases by 1 unit, y increases by 2.5 unit. And y increases because the sign is positive. So if x increases, y will also increase. There is a direct relationship. So next, how to know whether a regression model is a good fit to the model. For example, how well are your average weekly study hour explaining your marks? You will simply calculate a value which is called the coefficient of determination, which is simply the square of coefficient of correlation, right? So this coefficient of correlation tells us how much variation in a dependent variable has been explained by the independent variable. So let's see another example which will further clarify this concept. Suppose we have data on crop yield and the amount of rainfall. and y is equal to crop yield, that is, it is dependent upon the amount of rainfall. We have this data and we are asked that given this data on crop yield and amount of rainfall, fit a regression line and predict the crop yield. So predict, you always predict the dependent variable. So it's understood that the dependent variable is crop yield, because crop yield is dependent upon amount of rainfall. So you have to predict crop yield when amount of rainfall is 30 and if it is 40. So these are two separate parts. You have to comment on the goodness of the fitted model. That is how well the rainfall is predicting the crop yield. So first step, as I said, always make a scatter plot. You can see if you make a scatter plot that all the points are clustered around a straight line except for this point, which is an outlier. So we should delete this, right? So this value 21, 105, this pair is an outlier and we are not going to include this pair in our calculations. That's why when sum of x is calculated, this 21 is not included. Similarly, in sum of y, this 105 is not included. And similarly, we have discarded this pair from all the columns. So you calculate using the formula you just learned. And keep in mind, you are not using the outlier pair. And similarly, use this formula for the intercept that you have just learned. And you'll get these values of the intercept and the slope coefficient. And this is your intercept value. Now, how to know whether the model is a good fit, whether the rainfall is explaining the crop yield or not. R square, I just said, is the square of coefficient of correlation that you just did in the last lecture. If general viewers are not aware of the coefficient of correlation, you are strongly advised to watch the video on coefficient of correlation. So you calculate the coefficient of correlation and then square it up, right? And you will get a particular value. Okay, so this particular value 0.6891 or approximately 69%, you will say approximately 69% of the variation in crop yield has been explained by the amount of rainfall, which means approximately 31% of the variation in crop yield is due to some other factors that are not rainfall. Okay, now if we have to predict the crop yield based on the amount of rainfall, note that the minimum allowed value of, before I go for the prediction, note that the minimum value allowed for this statistic is 35%. Some researchers say 30%. That is, if you are given a model and you want to say whether it's a good model or not, you can, from exam point of view, you say minimum 30% or 0.30 is the answer. You can say it's a fairly good model. So how to know the threshold? These are the threshold for R square. These are the threshold that if it is up till 0.3, then it's a weak fit, between 0.6, medium fit, and so on. These are the thresholds given. Okay. Next, we have the prediction. We have to predict crop yield when rainfall is 30, or we have to find y when x is 30. From the above line, you just saw that the fitted OLS is equal to, pardon that the A part is missing here. Let me see. The intercept is 252.07, right? This intercept is 252.07. So the fitted OLS is 252.07 plus slope coefficient times 30. So you have calculated it. So expected crop yield is this much unit. Now, if the next part is if the crop yield when rainfall is 40. Now you have to keep one thing in mind. Go back to this data. What is the minimum value of x? 10. What is the maximum value of x? 35. So you can only do predictions if the given value is within this. That is, if in the first part you see that the given amount of rainfall was 30, which is between 10 and 35, okay, you can predict. But if the rainfall is 40, that is outside this value of 35. So you should say that we cannot predict for the amount of rainfall equal to 40 because this is outside the sample range. This concept is sometimes also called that regression is for prediction. It may not be very good for forecasting. There are dedicated regression model which are other like the time series model or auto-regressive moving average, not relevant to students of introductory statistics. What you should know is that regression is only used for prediction when the values or the value for which prediction is required is within the sample range. That is, it is within the minimum value of x and the maximum value. So here we end the lecture. This was all about the basic concepts of regression. To those students who are enrolled in introductory statistics course at NUST, this part is the end of your statistics course. The general viewer who want to explore more into the details of regression, I have a complete playlist of applied econometrics. You can watch those videos as well, or you can request for another dedicated videos on the complexities of linear regression, right? So with this, I hope that you understand, and you are welcome to watch this video more than once if there are still some confusion. I will also mention my email address in the comment section. I can send you these copy of these handwritten notes if you want to get, right? Thank you.